Very good afternoon, one and all. This is the first tutorial session of this ongoing 5-day Gyan course on all about wireless power transfer, antenna circuit device and applications. This tutorial session is basically divided into 3 different parts. First will be the scattering parameters fundamentals, followed by some numerical problems with S parameters, and the last part will be Smith chart fundamentals and its applications for solving the problems on the key component of WPT systems. It may be based on like few problems on antenna sides also. Okay, let us start the first part, that is fundamentals of scattering parameters. Here you can see what is happening. It is simply a two-port network. That you can correlate this as a black box, which is having one voltage current at the input side, one voltage current at the output side. This may have anything else, just like two simple block diagram. Okay, it may have passive circuit, passive elements, it may have active elements, may have hybrid, may have lumped parameters or distributed parameters, operated at low frequencies, operated at high frequencies. Because what is inside this one, how this traditional two-port network will fail when we operate a signal of very high frequencies to that one, and how to resolve that two-port network characteristics while considering the concept of scattering parameters. Just see this one, same thing means this may have passive components, that a combination of resistor, capacitor or inductor. Active components may have hybrid one, or last one is more important rather than to this one, because when we observe a system or a network at high frequencies, then distributed or lumped parameter characteristics is more important rather than to the this other ways of component. That's why last classification is more important for us. Here review means, like, just see this one, that is Z parameters characteristics, that we take it in the form of like input current, output current are independent parameters. Here voltage that we are considering as a dependent one, that V1 is the function of I1 I2, V2 is the function of I1 I2. Same thing in Y parameter, current I1 is the function of V1 V2, I2 is the function of V1 V2. In hybrid, that will be one current, one voltage, V1 I2 in terms of I1 V2. And in ABCD, that is known as the transmission parameters, also complete input port in terms of other port. That is, and then how these are linked, that here you can drive the Z matrix, here you can drive the Y matrix, here you can drive the H matrix. In the same way, how it is written? It is written as V1 equal to A V2 plus B I2, I1 equal to A V2 plus C I2. Okay, then ultimately similar concept you can apply for driving the matrix here. Here, just see that one, each and everything we are defining in terms of voltage as well as the current. Okay, while making how to calculate these parameters, for that one we need to make this parameter 0. Product of Z1 to I2 to be 0, it is two possibility, A dot B equal to 0, AB equal to 0, either A equal to 0 or B equal to 0. Okay, but if you make Z1 to equal to 0, it may like not favorable condition, because that is unknown parameter that we need to drive. That if you are intentionally making unknown parameter 0, then what's the meaning of including that parameter? It means Z12 can never be equal to 0 in Z12 I1 equal to 0. Okay, then I2 equal to 0, then there may be a possibility of making I2 equal to 0. it may be a condition that I2 equal to 0, that port may be open circuit. Then open circuit condition will make current equal to 0. That is feasible. Okay, same condition we apply here. Then ultimately, while making input port or output port 0, you can find out these parameters. Okay, same way, if you are making, you need to make the voltage 0, V1 or V2, voltage will be 0 if you are applying the short circuit conditions, either input port or output port. In that way, then you can easily calculate Y11, Y12, Y21, Y22. Same thing here, I1 is to be made 0, it means input port should be open circuit, and V2 is to be made 0, then output port should be short circuit. Okay, then ultimately that fundamentals we can apply here for calculating that parameter. Like I2 equal to 0 means Z11 input impedance is a ratio of V1 upon I1 when I2 equal to 0. Okay, then same Y parameters, then H parameters and ABCD parameter you can write it easily. Okay, in all these four cases we have applied the condition of open or short circuit. Okay, either you are making open circuit condition or short circuit condition, but in if the same system is operating at high frequency, then both the conditions are critical, both are dangerous if you are not taking them seriously, open circuit conditions as well as the short circuit condition. In low frequency there is no meaning of that one, it may be easily managed, but when the same block, if the same block is operating at high frequency, then you need to be very much careful at the moment when it is open circuit or short circuit one. Okay. Now summary of these parameters for this way, then input expressed in terms of this one, some of them just overview I have discussed in last slides, and remaining other parameters are also there, but all these parameters are open circuit or short circuit parameters. Okay, there should not be any doubt in that way, because in undergraduate these two port parameters are well studied somewhere in basic electrical engineering or some higher semester course. Now condition is that once we are having a well matured two port network theory, drive a different kind of two port network theory, that questions should be there somewhere in the mind, then we'll give some explanation to that way. Unfortunately, conventional input parameters do not have a very obvious physical meaning and are also difficult to measure directly at high frequencies because of certain reasons. What is the first reason? That traditional two-port parameters are based on measurement of voltage and current, but in high frequency we always play with the power, incident power or reflected power. Okay, then voltage and current measurements are difficult to measure directly at microwave frequencies. Power meter will be there at high frequency power meter, but generally we don't prefer to have the measurement facility at high voltage measurement, current measurement at high frequencies. Okay, that is the first reason. Second point is the Z matrix requires open circuit conditions, and it is hard to create an ideal open circuit, because when these two terminals are open, look wise these are open, but there is some parasitic capacitance happening when this conductor and conductor is isolated with air. Through air one capacitor is formed, that's why you cannot replace that one, you cannot make that capacitor response ideally 0. It means physically you are seeing that these two are open circuit, but really it is not an open circuit, it is creating a leakage path to that way. Okay, that is the capacitance. It is hard to create an ideal open parasitic capacitance. Then likewise Y parameters require short circuit conditions. Okay, when you are making a short circuit condition, then again it will be a problem. Again ideal shorts are impossible at high frequency due to the finite inductance. That is the another reasons. And the last one, that's short circuit and open circuits are difficult to achieve over a broad band of frequency, because in high frequency we need to play with the frequency, not with the voltage. In like in traditional power systems, in core electrical engineering, the reverse phenomena is there, that people who belongs to core electrical engineering, they used to play with the variations in the voltage at constant 50 Hz frequency. But here in communication and high frequency systems, we need to have the constant voltage, but frequency will vary for a wider range of condition. Then for creating open circuit and short circuit condition for wideband, ultra wideband, super wideband, then it is quite impossible to create in the high frequency system. These are the few points, and many active devices could oscillate under the open and short circuit termination, that you can recall standing wave patterns behavior. That short circuit and open circuit condition, generally in transmission line theory we study that one. Okay, that is also occurs when we apply the open and short circuit termination to this way. Active devices such as power transistors or tunnel diodes very often will not be short or open circuited. Stability is another issue. Okay, that systems will not be stable, or that active devices will not be stable conditions if you are applying that open and short circuit condition. Now to remove these limitations, or to overcome, not remove, to overcome these limitations, that another way of equivalent to two-port, traditional two-port network is to be derived, that is known as the scattering parameters, or simply S parameters matrix. That S parameters are easier to measure at high frequencies. The measurement is direct and only involves measurement of relative quantities such as standing wave ratio or the location of the first minima related to that load. Okay, that is easy as compared to measuring the voltage and current at high frequencies. Just see two-port network. Okay, then it's equivalent to this S matrix. In S parameter, Z parameter, it was Z11, Z12, Z21, Z22, representation of that one. Okay, at low frequency, that V1 equal to voltage at port 1, I1 is current at port 1, V2 is voltage at port 2, I2 is current at port 2. At high frequencies, V1 will be incident voltage at port 1 plus reflected voltage at port 1. It is not like this. At high frequency, same two-port network, it will have two components. One is incident at port 1, second one is reflected from that same port 1. Same way, current will be in the two way, one is incident current, second one is reflected current. Same thing you need to apply for the other port also, second port, port number 2. And finally means, just see that one, incidence and reflection, two different notations. Either you can proceed with this notation, or easiest way to represent that incidence and reflection at port 1 and port 2 in this way, that A1 is the incidence at port 1. That incidence may be current incidence or voltage incidence, that is different issue. Okay, then B1 is the reflection from port 1, A2 is the incidence at port 2, B2 is the reflection from port 2. Then just see this one. Two wire transmission line, that yellow means that is transmission line point, that is one end, one port, another port, input is fed to this one and to get the output from that way. That port 1 and port 2, this is the incidence. Okay, then ultimately, then reflection from port 1 will be like this, that a power is incident to that one, a certain amount of power will be transmitted forward, and the difference of these two due to mismatch between this port, this side to this impedance at this point. Because at high frequency, we need to be very much careful about the matching. If there is no perfect match, then ultimately the situations will be entirely different. Okay, then it will be certain amount of power will be reflected back to that way, that parameter S11 B1 upon A1, B1 is reflection at port 1, reflection from port 1, A1 is incident at port 1. Okay, the same thing will be happening here also. If you do incidence at port 2, then reflection will be from port 2 in that way. Okay, then ultimately that from this side to this side will be the insertion, and from this side to this side will be the reverse condition, and we can summarize these four parameters, that is S21, S12 from this side, B1, B2 in terms of S parameters, S11, S12, S21, S22, A1, A2. S11 is input reflection coefficient, reverse transmission coefficient, forward transmission coefficient, or output reflection coefficient. For making it easy to memorize, simply remember IRFO, IRFO. I for input, R for reverse, F for forward, O for output. That same notation is applicable to traditional two-port network also. In Z parameters also same notation, IRFO will be applicable, but there it will be in terms of impedance. In case of Y parameter, that same notation will be used for admittance. Okay, that is that ultimately we can define these four parameters in this way: input reflection coefficient, reverse transmission coefficient, forward transmission coefficient, and output reflection coefficient. How these parameters will be measured? As parameters are measured by sending a single frequency signal into the network and detect what waves exist from each port. That is like this two-port network. Okay, then what to do? Make port 2 perfectly matched. Matching is equally important, that I already told you. It should be perfectly matched, terminated with standard load 50 ohm or 75 ohm something. Okay, that will make it perfectly matched. And what is happening to that input side? When we are making that output port perfectly matched, then what to do? That you need to apply some power at the input port. Then what will happen? This is the incident wave at the input port. Output port is terminated. Okay, there will be no reflection from output port. Okay, then a wave will be reflected back, because this is not perfectly matched. That's why from this source to this side it is some mismatch. That's why this reflection is taking place. Then a difference of these two will be going outward from left to right as a transmitted wave. That is the conditions when you are making port 2 is perfectly matched and applying incidence at port 1. Same thing will happen when you do the process for other port. Just see this one. Port 1 is perfectly matched, and port 2 you are exciting with some incidence, like this one, incident wave A2. Port 2, a part of that one will be reflected from port 2, and the difference of that one will come to the port 1. That is the things and that we can easily do in the laboratory environment. Okay, here just to like defining that how to take that one, S11 equal to B1 upon A1, S12 equal to B1 upon A2, S21 and S22. In case of like equations, we can write this way, and other way that B1, B2 in terms of A1, A2 with this S parameter matrix, and in simplest way we can write in this way also. Like this is all three cases are having the same meaning, including this one also. Now S11, how we have calculated? Same things that we have applied in case of Z parameter, Y parameter. That was, we need to make A2 equal to 0. A2 is what? Incidence at port 2. It means if there is no incident at port 2, then it will be defined as B1 upon A1. A2 equal to 0 does not mean it is giving a sense of you open circuit or short circuit. It is giving a sense of there is no incidence at port 2. Okay, then it is defined as reflected power wave at port 1 to the incident power wave at port 1. Then S21 B2 upon A1, again A2 equal to 0. Then transmitted power wave at port 2 to the incident power wave at port 1. That is, these two parameters are calculated while making A2 equal to 0. That is, port 2 is perfectly matched. Same S22, S12 in this way, then ultimately it will be A1 equal to 0, port 1 is perfectly matched. That is S11, S12, S21 and S22 you can easily calculate to that way. Now coming to the n number of port, because we cannot restrict ourselves, like antenna is a single port, single element antenna is a single port device. When you talk about MIMO, it will have multiple port. Then same thing may happen to other, if you are having a filter, then ultimately one input port, output port, two port will be there. Then how to tackle more than one port in S parameter? That concept you can think here. Here port 1, 2, 3, 4 up to n number of ports. Then this S parameter matrix will be like this 1 1 1 2 1 3 up to 1n, then 2 1 2 2 2 3 up to 2n, like this. Okay, then you can take it in the simplest way, that if it is a one port, then only S11 will be there. That's why in your single element antenna you always plot S11. S12, S21, S22 will never exist in a single port antenna. Okay. Then ultimately, if you are having two port, then this matrix will be two port, means in case of MIMO systems that you take ultimately that S11, S12, S21 and S22, and certain like conclusion you gives in S11 values and S22 values, and certain conclusion you give in terms of S12 and S22 values. Similarly, if there is a three port, then S11, S12, S3, this will be four port. Okay, coming to that one, because in several things you have seen that antenna as a element of rectangular systems. That same S parameter concept will be applicable to that one, because S parameter concept in antenna used in X application, Y application, Z application is not going to change. It will remain as it is. In this way, what is happening, that simulated and measured performance that you are seeing here, it's a part of this paper that I have just plotted here, just to give you the sense of S parameter, that S11 is the reflection coefficient. Okay, always remember that if you are representing y-axis x11 s11 in terms of dB with negative value, it will be reflection coefficient. But sometimes in locally published paper or some not authentic reference, you will mark that one as a return loss. Return loss is having some different meaning rather than to the reflection coefficient. Return loss in negative values, there is no meaning. You can correlate that one while converting into that linear scale in terms of ratios of B1 upon A2, something like that. Okay, but reflection coefficient with some negative values, take it in antilog, then you will realize that what is happening to the linear scale. That is possible. For this particular geometry, that is the top radiator and that is the backside metasurface of that one. And ultimately, these values like S11 for this one, 45 minus 45 dB at 3.37. 45 dB means that is measured values, this one 45 dB. Okay, then minus 45 dB, minus 40 dB, minus 35 at linear scale will not be more different. Okay, in dB scale, you are seeing that difference of minus 10 dB, minus 15 dB. Okay, then you can correlate that minus 10 dB in linear scale, minus 20 dB, minus 30 dB. You try to convert that one in linear scale, then you will realize that how minutely values are changing in linear scale, but drastic behavior you will observe in the logarithmic scale. The same thing will happen because minute variations in bigger scales as well as bigger variation in minute way, both the ways are very easy to represent in dB. 35 dB to 40 dB, only 5 variations. You convert that in linear, then you will see the huge difference. That like this one, minus 30 dB to minus 40 dB, look wise it's minus 10 dB, but in linear scale it will be very small. Okay, that is only the beauty of dB representation that we always prefer to in all electromagnetic problems. Like S11 equal to minus dB means how 10% you may convert it into linear scale, then you will realize that one. Okay, then 10% of the incident power is reflected and 90% is radiated from the one port to that other way. That other way means multi-port MIMO systems. Then you can think about that minus 10 dB S11 values, S21, S31, S41, something like that. Okay, then because it is a 4-port one, then 4-port means total 16 values of S parameters may exist. Okay, but due to some matching condition, several parameters we always ignore. We take only S11, S12, S21, S31, S41, something. Okay, because S11 and S22, S33, S44 should have the same behavior. Okay, S13, S31 must have the same behavior because we are considering that symmetry in that way, and we always prefer to maintain that one in MIMO system. Okay, then now how to calculate A1, A2, that is incidences and reflection in terms of voltage and current. because in laboratory we will have the voltage and currents available easily. Then how to convert that equivalent to that incidence and reflection, we will see here. Just see a two port black box, port 1, port 2, source impedance and load impedance. If Zs equal to Z0, Z0 equal to Z, Z0 is what? Characteristic impedance of this block. Okay, then there should not be any doubt that how to define that characteristic impedance. ZL equal to Z0, that is load is perfectly matched. Okay, that is input to output side, there is no reflection to that way. Now I incidence current at port 1, IR is the reflected current from port 1, then incidence voltage at port 1, reflected voltage at port 2, then total voltage at that input port will be summation of these two. Total current will be, why not summation, it is difference, because if we observe the behavior of incidence voltage and reflected voltage, reflected voltage will be in same phase to the incident voltage, while reflected current is always opposite to the incident current. That's why when we represent the summation of incidence and reflection in terms of voltage, it will be always summation plus sign, and in case of current it will be the difference of these two. That's why it is considered V1 plus VR equal to V1 and I1 minus IR equal to I1 net. Z0 equal to Vi upon II equal to VR upon IR. Then put this value. Now equation 2 becomes this one, I1 equal to V1 minus VR upon Z1. Rearrange this one, V1 Vi minus VR equal to I1 Z0. Then do the same process while adding equation 1 and 3, because here you are having a summation, here you are having a difference. Then you can calculate easily Vi in terms of, Vi means what? Incidence in terms of supply parameters. V1 is what? Supply parameters available to you, V1 and I1, that is available to you. Then incidence in terms of source parameter that you have derived here, and do the same process for port, taking the difference of these two equations, then you will get VR equal to this one. That incidence in source and reflection in source that you have obtained here. Now what to do? Now A1 equal to square root of Vi square upon Z0. Vi square is what? V square upon R is what? Power. V square upon R, I square of R, Vi. These are the power terms. Okay. V square R, V square upon R and I square R. In these two cases, R is common. It means that power is directly proportional to the square values of excitation. In V square R, excitation is V. In I square, V square upon R, excitation is V, and I square R, excitation is I. Okay, if we ignore that particular load resistance, then power is basically the square values of that excitation. Then taking that one, if you take the square root of that quantity, then ultimately you are getting the incidence in that way. And finally means take, because Vi you have already calculated and you put this value here, then you will get A1 equal to this one and B1 equal to this way. That is same thing for port 2 will be in this way, like A1 B1 A2 B2, right hand side you are having each and everything related to your source available. V1 I1 Z0 is also known to you. Here also V1 V2 I2 and Z0 is also known to you. It means corresponding behavior of voltage and current we have obtained in terms of incidence and reflection at both port 1 and port 2. Now S11 equal to B1 upon A1, when A2 equal to 0, put this value simply, then you will get S11 equal to, just rearranging this one, Z1 upon Z1 plus Z0 upon Z1 minus Z0, where at input port V1 upon I1 ratio can be replaced by Z1. Okay, at input side, then same for output port, you will get this one. Now return loss will be minus 20 log base 10 S11. Okay, this behavior will should always be in positive. That is, then it is meaningful. Okay, then you can convert this one in the linear scale, as convert that reflection coefficient dB value into linear scale. Then you will realize that one is feasible, another quantity will not be feasible if that plus to minus sign is changed. VSWR in terms of parameter, that is Vmax upon Vmin. Do Vmax is nothing but that is the summation of these two, and Vmin means the difference of these two. Everything is given to you 1 plus k. K is the reflection coefficient upon 1 minus k, and k may also be that is mod of S11. S11 is what? That is reflection coefficient, input reflection coefficient. Taking mod, ultimately you are considering that real part of that one. Otherwise, inherent behavior of S11 will be the complex. Okay, when we consider the magnitude, then we always take the mod of that quantity. Then just see this one, what is happening, same as parameters, S11, S121, S12, and this way. Then B1 equal this equation that we have calculated, then A in terms of source, this one. Okay, then other way for representing this way for port 1, port 2, then we have taken this way power wave traveling towards the two port, that is A square. Traveling means that is incidence, and the power wave reflected back from the two port, that is B square, mod of B square. Okay, then S1 square is nothing but that is power reflected from port 1, S22 square power transmitted from port 1 to port 2, then power transmitted from port 2 to port 1. Then A, B and S are effective values, not peak values of the corresponding sine functions. What S parameter depends upon now means that is important, means what things can make changes the S parameters. Okay, this black box characteristic should be changed, and what parameters are responsible for that. If the network is changed, then the S parameter changes. Network is changed means earlier you have a pi combination, you replace with p combination, then the entire parameters will be changed. That is that one. Okay, earlier it is RC circuit, then you are replaced with LC, then definitely the parameters will be changed. If the frequency is changed, because inherent behavior of all S parameters is frequency dependent, then frequency change, source parameters are fixed, but you are changing the frequency, source frequency, then definitely that S parameters matrix will be changed. Third one, if the load impedance is changed, then automatically S parameter, because load impedance is changed means change will occur in terms of mismatch of impedance, output impedance, output port impedance to the load impedance. If it is perfectly matched, then output reflection will come in the different way. If it is mismatched, then reflected amount will be different to that earlier case, and that will make the entire process change. That's why the S parameter matrix will change if the load impedance is changed. If the source impedance is changed, then again S parameters will also be changed. Okay, so these are the few observations to make the S parameter change. The dependency of S parameters in a two-port network. One is either source dependency, load dependency, source frequency dependency, then network dependency, network behavior dependency of that parameters. Here S parameters are generally quoted with source and load impedance of 50 ohm. 50 ohm is the standard frequency, load for that one. Then there may be a certain justification behind this 50 ohm, was generally available in several textbooks and UG also, that coming to that parameter conversion, like S parameters in terms of Z parameters, that is feasible. Okay, no need to do that conversion directly. If possible, you should know the process of this conversion. No need to memorize this thing, and always it is very easy to memorize the process rather than to memorizing the entire mathematics to that way. Then Z parameters in terms of S parameters. Here S parameters in terms of Y parameters for two port. Y parameters in terms of S parameters. Okay, then S parameters in terms of H parameters, then H parameters in terms of S parameters will come in this way. And this is the, because all these values, small letters are used here, these are the normalized values. Okay, These are S is small, Z is small, S is small, Z is small, Y is small, then H is small, all. These are the normalized value, actual values divided by characteristic impedance. That is this way. Okay. By using this one, then automatically this conversion will take place. Without S1, rest of the conversion we always prefer at low frequencies. Z to Y conversion, Y to Z, ABCD to this one, that one. But because we need to have the entire discussion in S parameter, that's why that conversion is also equally important for us. Now, how to calculate these parameters online? That I have got that reference. You can use this link, okay, and in that way you can quickly calculate the S parameters corresponding to each characteristic impedance. Give that values, then automatically it will calculate, it will give you the instant answer rather than to doing the manual calculations to that way. Okay, then here performance parameters in terms of S parameter, that return loss, that will be defined in terms of 10 log base 10 pi upon pr. Return loss, the incident power to the reflected power, that will give you the return loss, and ultimately reflected power upon incident power is the reflection coefficient. Then this ratio will be represented in terms of 1 upon gamma. Okay, then ultimately 1 upon gamma is nothing but that is 1 upon S11 value. So these are the three different ways for taking this one in the form of reflection coefficient. Okay, then transmission or attenuation in dB, that is 10 log base 10 log. By default it is base 10 pi minus pr upon po. Okay, then here take po common, then ultimately it can be replaced in terms of S parameters like this 1 minus 10 log 1 minus mod of S11 square upon mod of S12 square. Return loss dB 10 log pi upon pi minus pr, 10 log 1 upon 1 minus mod of S11 square. Insertion loss, that is another important parameters, insertion loss, because in between source to load, if you are inserting another block, then what effect will come due to that one after inserting that thing, pi upon po output power, then ultimately it is in terms of then voltage standing wave ratio in terms of S parameters, that can be written in this way. This is the way return loss in terms of this one. Vice versa will be possible in this way. Reflection coefficient in terms of return loss, that is anti-loss or that way. Okay, that we can do it easily. Reflection coefficient in terms of VSWR, then reflected power, then mismatch loss, then forward powers. All these parameters are important when we solve the numerical problems. Hopefully, in the end of this first part of this tutorial 1, that is summary. Summary of this experiment, the transmitted and the reflected wave will have changed in both amplitude and phase from the incident wave. That is absolutely correct. Generally, the transmitted and reflected wave will be at the same frequency as the incident wave. Frequency will not be changed. Okay, frequency will change if there is a moment of that, like Doppler shift or something will happening to that way. As parameters are complex in nature, their complex quantities have magnitude as well as angle, because both the magnitude and phase of input signals are changed by the network. That is why they are sometimes referred to as the complex scattering parameters. These four parameters in case of two-port network actually contains 8 separate numbers, real and imaginary part, 4 are magnitude part, 4 are phase part. Okay, S11 is having mod of S11, angle of S11, the total 4 variable, four variable, total 8 parameters will be existing to that way. Then quite often we refer to magnitude only, as it is the most, it is of most interest how much gain or loss, that is way to define in terms of magnitude only. Okay, then ultimately we prefer to have more important than how much the signal has been phase shifted, because that phase shifted concept will come in the visual information. If in the case of that way magnitude is concerned, then ultimately we prefer to have the reference of magnitude only while defining the term gain or loss of power, gain of how much gain we are achieving and how much power is lost. Okay, some metrics are symmetrical, asymmetrical. Asymmetrical matrix has symmetry about the leading diagonal S12, S21, like that. In case of a symmetrical two-port network, if you are having S12 equal to S21, then you will call it symmetrical condition. And all MIMO structures that we have, the by default symmetry. If there is a mismatch in S12 and S21 value, then you have made something wrong, which is not fulfilling the physics behind that one. Okay. Interchanging the input and output port does not change the transmission property. A transmission line is an example of a symmetrical two port. Two wire is there. This is the length of that wire. Interchange that one, there will be no change because the overall structure of each wire is symmetrical. If that structure, this wire is not made of symmetrical deposition of that one, then the behavior will be changed. But in generally, we use that symmetrical orientations of all the atoms and molecules, and that's why we prefer to have this way. And leading diagonal S parameters S11, like this was that leading diagonal, that S12 and S21, here S11 and S22, these are known as the reflection coefficient because they refer to the reflection occurring at one port only. There ultimately off diagonal parameters S1 to S21 are referred to the transmission coefficient. One is forward transmission, second one is reverse transmission. That's why IRFO term, forward for one parameters, then reverse for another parameters is coming into the picture of that way. Then these are the few references that we can take it. If you need the deep study, then you refer to these three references in volume 1, volume 2 on especially on the test parameter. If you are not able to download, I am having the soft copy of all these three volumes. May drop a mail to me, I will share to you all. This was the theoretical part of this one. We can move to the few numerical before taking a short break of 5 minutes. Till now, if is there any query, then you can discuss. Otherwise, we can go directly for the numerical problem. Any doubt? Okay. Then that is the second part of this tutorial session. That is, after having a discussions on fundamentals behind the scattering parameters, let us solve some numerical problems that will give you an idea of applying the test parameters on the problems associated with different components of that WPT systems as well. The first numerical that you may note down if possible. Okay, the 50 ohm microwave integrated circuit amplifier. Amplifier means same microwave amplifier what Professor Naoki has discussed in the last two lectures. Same high frequency amplifier, high frequency amplifier. High frequency amplifier for low power, high frequency amplifier for high power. That is the two different variations of that way. Okay, then it is a S parameter characteristics of that high frequency high frequency amplifier, that S11 is 0.12 angle of minus 10 degree, S12 equal to 0.002 angle of minus 78, S21 and S22. What to calculate? Input VSWR, then return loss in dB, reverse insertion power loss, linear as well as in dB values, then forward insertion power gain, linear and dB values. Here, these are the formulations. Take couple of minutes shortly and try to solve and give me the answer. That is VSWR, put simply 1 plus mod of S11, 1 plus 0.12 upon 1 minus 0.12. Solve that one quickly to give me the answer. What is the value of A part? 1.27. Okay. Then return loss, not possible to solve. It needs scientific calculation. Reverse power gain, that is 20 log base 10 mod of S12, forward 20 log base 10 mod of, that you can note down, that later on while going back to room you can verify. Here it is double B, you can take it, consider a single one. Then you can verify these values while putting into the given this formulations. Moving ahead, another set, they are given S11 equal to 0.1 and you need to find out return loss. Simply you can put here and you will get the answer of 20 dB. Just see this one, 20 dB in linear scale it is 0.1. S11 is what? A1 upon B1 or B1 upon A1? B1 upon A1. Then put B1 upon A1 equal to 0.1. Then you can easily correlate what is the meaning of that way. Take other set, S21 equal to 0.5. Find forward gain in dB. That is simply you put this here minus that S21 0.5 values in dB is minus 6.02. Then power, input power 1 watt. Find power delivered to load, that for one formulation was there, 1 into 1 minus P in square, mod of P in square, then it will be 0.96 watt. Just see this one, 1 watt input and finally at load it is coming 0.96 watt. 0.04 watt is lost somewhere in between, that is okay. Then another one, S12 equal to 0.1, then isolation, that is minus 40 dB. In linear scale that is very small, but in logarithmic scale it is giving a large number, that is minus 40 dB. Okay. S21 3 dB, minus 3 dB, then voltage ratio V out upon V in will be 0.707, that you can easily calculate with the given set of those equations. Then S11 equal to 0.5, 0.05, S21 equal to 0.95. This S is not there, this is not S, it is typos. S11 equal to 0.05, S21 equal to 0.95, S12 equal to 0.2, S22 equal to 0.2. Magnitude means that phase part is not given, then you can find out return loss at port 1, forward gain and incidence, that will be in this way. Then insertion gain, oh, then solution for this one, that the solution for this first part is this one. Okay, for this part it is S21. Where is S21? Where is the solution of this one? S21, no. Oh yes, S21 equal to 10 to the power 10 upon 20, that is 3.16. Then another, a 2-port amplifier has the following S parameters at certain frequencies. This is that power gain equal to 20 log base 10, that is, then you can calculate is 7.96 dB. That is ultimately a set of some numerical problems. Then same things we can explore in core antenna related problems, Corn filter, then ultimately for other high frequency devices or circuits. Okay, then again the same reference we will use for this particular topic, that is scattering parameters, okay, or simply S parameters. Now this was the last of this way, and we will, it is exact 4 o'clock. We can have short 5-minute gap before coming to that next part of this one. The last part of this tutorial session is the Smith chart fundamentals and its applications, because on several uh, occasions of last couple of lectures, Professor Naoki Shinohara have given you the different way of representation of a Smith chart also, and several analyses have also been made in terms of S parameters. That's why intentionally these two things are included in the tutorial session to make the things clear, fundamental things clear behind that scattering parameters as well as that Smith chart. Let us start this way. Look at this complicated graph which we prefer to use at high frequencies. Okay, it is having certain meaning of these lines coming at the center of some circles on this x-axis, as well as some are going outward and the bottom side, and all three scales are having certain meaning. Entire high frequency systems can be represented within this single Smith chart, entire one. Okay, because generally we do the measurement at low frequencies with the help of your multimeter as an analytical values. Multimeter gives you the analytical values of any quantity, voltage, current, or same parameters you measure with the help of CRO also. But CRO gives you the graphical representation of parameters. Numerical values, analytical values, and graphical values. That is the way. Okay. Then here ultimately this is the more or less similar to that graphical representation of entire things, that when that systems is operating in the high frequency, that is very easy to represent that things on this graph, what we call as the Smith chart. Let us go to the brief history, few lines of this Smith chart, that it came into in 1939 by P. Smith at Bell Telephone Laboratory, United States. Okay, the Smith chart has been introduced to reduce the tedious manipulations involved in calculating the characteristics of a transmission line by means of a graphical representation. Transmission line problem does not mean that it will not be able to solve the antenna. Antenna is a specific case of transmission line. Okay, don't forget that one. It is coming from the transmission line concept. A Smith chart is graphical tool which is very useful for solving transmission line problems. Then Smith chart is a mapping between the normalized complex impedance, that is uh, real impedance divided by characteristic impedance, and the complex reflection coefficient. Reflection coefficient variations will be 0 to 1. 0 reflection coefficient and 1 entire complex planes will be existing between these two values, and this way that is impedance will go from 0 to infinite way. Okay, then a Smith chart is essentially a plot of voltage reflection coefficient in the complex plane. It can be used to convert from voltage reflection coefficient to normalized impedance or admittance, or vice versa. Both the way it can be used. It is a more generic graphical representation. It can be solved to represent the reflection coefficient in terms of impedance, or impedance in terms of reflection coefficient in terms of admittance, admittance in terms of reflection coefficient. All the way are open in a Smith chart. A Smith chart consists of a polar plot, okay, of reflection coefficient onto which the overlaid circles of constant, that's standard plot, is reflection coefficient less than equal to 1. Entire things will be within that unit circle. Okay, then Smith chart is representation medium in several advanced softwares including CAD design, microwave CAD. That in that way that Smith chart play a significant roles. Starting from that fundamental concept that you are having parameters like reflection coefficient magnitude, reflection coefficient phase angle, length, all these parameters can be easily plotted on the Smith chart. That few parameters I'll show you here, and the rest of the things you can study yourself, like inductance, resistance, and capacitance. Inductance ZR equal to R, capacitive inductive reactance ZL equal to J omega L, then ZC equal to 1 over J omega C or minus J upon omega c. Okay, in this way, what should be the range of R, ZL or ZC? R resistance will go 0 to infinite, inductance will also go 0 to infinite, capacitance will also go 0 to infinite. Inductance will directly affecting the inductive reactance because ZL is directly proportional to L, but ZC is inversely proportional to C. Infinite capacitance will give you a zero reactance because 1 over 0, 1 over infinite will be 0. Okay, then ultimately it is in this way. Now, how to represent this linear scale 0 to infinite behavior on other representation? Just see what is happening here. All values 0 to infinite for this resistance will go from this 0 point to this real axis. Infinite resistance, different values will come, all values will exist only on that x-axis. Here it is positive, there is no chance of having the negative values when you are changing the inductance. It means all values corresponding to ZL or inductive behavior will exist on this positive y-axis, and our capacity behavior opposite to this one because of minus sign, it is existing here. It means these three different behavior we have segregated on the two-dimensional plot. One is in on linear on this real axis, and on positive imaginary axis and negative imaginary axis. Okay. Then ultimately we need to take the reference of this concept here for plotting, that a transmission line with characteristic impedance 50 ohm is terminated into the following load impedance, that is equal to this one, short circuit, that is equal to infinite, that is equal to 50 ohm, ZL is complex values 16.67 minus J 16.67, then ZL equal to some different value 50 plus J 150 something. Okay, then this is the formulation for calculating the reflection coefficient, that you put these values to find out 5 different values of reflection coefficient. Okay, 5 different representation of these impedances in terms of 5 different values of reflection coefficient. Gamma naught equal to -1 for ZL equal to 0. Gamma naught equal to 1 for ZL equal to infinite here. Then gamma naught equal to 0 for ZL equal to 50 ohm. Gamma naught, because here two complex quantities are there, that's why two complex values of reflection coefficient are coming. ZN gamma naught equal to 0.54 angle 221 degree for this one and two. Then how these values are plotted in the polar form, that is this way. This was the transmission line for 4 different conditions. Now all values are existing within this unit circle, all impedances. It is having a different way, 0, infinite, as well as the complex conditions. All values are easily represented here in this way. Okay, gamma naught equal to 0, gamma naught equal to -1 will be this point, gamma naught equal to that complex point 1 is this one, another complex point is this one, and gamma naught equal to +1. Okay, then all variations of impedance between 0 to infinite are accommodated within the unit circles. Okay, that is the concept of representing this behavior, linear behavior into that polar form. Now coming to that discussion on normalized way, that this is that impedance, same transmission line section, which length is L, and this is an input side, then load is terminated by ZL, then reflection coefficient will be this way. The inherent behavior of this one is complex, that's why it is represented as real part as well as imaginary part. Then gamma naught equal to gamma naught R plus J gamma naught I. The other way of this one, you can take it in this form also, complex quantity x plus Ji can be represented the mod of that x square plus y square and angle of tan inverse y over x. That is the normal mathematical form of representation, that is in this way. Then input reflection coefficient, this formulation is also there in transmission line theory. Again, gamma d is having two part, real as well as imaginary. Then you make it impedance in this way. Okay, then finally in for d distance, because impedance at this point from load to L distance. This is the impedance from load to L distance, this side. Generally we take the impedance from source to load. It is the reference point is load to L distance that we are calculating. Then this factor is coming. Then divide this one into with characteristic impedance, then you will get this one, because taking this side, then Z in D upon Z naught equal to 1 plus gamma D upon 1 minus gamma D. Then gamma D values that you have calculated, this one, put this value here, do some rearrangement in this equation, then finally you are getting two set of circles. One is R values, that is real part of this one, and another is imaginary part of this equations. Okay, that R equal to this one, equation 11 and 12, imaginary. Now we need to focus, we need to plot these two cases separately. Separately, then we will merge within the common platform, then it will look like to that Smith chart what I have shown you in the first slide. Just see this one, equation number 11, then rearrange this equation, then rearrange this equation, then put R equal to 0. Just see this one, 13. This is what, imaginary or equation, which one? Oh, sorry. We are considering this equation R equal to something and X equal to something. Okay. Then this is R equal to this way. Then ultimately it is to be replaced by that standard circle equations by rearranging this one. Then R minus A square plus R minus B, where A and B are the center point of that circle and C is the radius of that one. Correlating this one, then A is nothing but R upon R plus 1, that first center point, and B is 0 and C equal to 1 upon R plus 1. Now you put A R equal to 0, then what will be the A value? 0 upon 0 plus 1. 0 upon 1 will be 0. 0 upon 1 will be 0. Then first center point is 0. Second center point was by default 0. Because there is no B component here. B equal to 0 from this one. It means center point is 0, 0 for a circle of radius 0. R equal to 0. Okay. And this one, radius is 1 upon 0 plus 1, 1. It means you need to plot a unit circle at center point 0, 0. That is the meaning of R equal to 0 plot. Take R equal to 0.5 and R equal to higher side, then all these circles, the center point will remain this x-axis, and at the moment when you are reducing that value or going towards that both the side, R equal to higher side also, and do the reverse in the reverse also, then the extreme point R equal to infinite, you will get 0 radius circle. It means all these resistive circles are existing, are centered at that x-axis. Okay. Then this one is, outer one is R equal to 0 circle, and this one is unit circle, which is plotting in the half plane, complete half plane of this one, R equal to 1. That is the reference way. And here what things you are getting, it is perfectly matched. Coming to that other way, plot of reflection coefficient, that is R equal to this one. Then just see what is, yes, that for this means what, that is X equal to something equation. Okay. Then ultimately center point is R upon 1 plus R, radius is 1 upon R plus 1 upon 1 plus R. Then converting this into this standard circle equation, then ultimately R equal to 0 is this one, R less than 0 to 1, all circles will be like this. Then R equal to 1 is this circle, R equal to 1, and when R is greater than 1, then all circles will be inside that way. Okay. Then two things, when R equal to 0 is this outermost circle. Okay. R is varying between 0 to 1, then all circle are in this region. Okay. But all that this point to this region circle will be R equal to that 1. Okay. then r greater than 1, all circle will exist inside this region. As the value will increase, then it is going towards the infinite radius point, and this point becomes when r equal to infinite. Okay. Coming to that other equation 12, that was x equal to something, imaginary part of that equation. Do the same arrangement, then ultimately it is having a equal to 1, b equal to 1 upon x, and c equal to 1 upon x. Okay, then change x values from 0 to infinite, x equal to 0.5, then a is 1, 1 upon 0.5, what, 2, 1 upon 0.5, 2. It means center point is 1, 2. Okay, and radius is 1 upon 0.5, that is 10 upon 5, 2. Okay, then where it will be that? It is existing, what is that center point? 1 and 2. From this point, 1 is here, and it will come outside this region when you will be able to complete this circle, this one. That is outside that one. But you need to take within that unit inside. That's why we are considering this behavior is sufficient for representing a reactive circle of x equal to 0.5. No need to take that entire one. Then take it other way, x equal to 1, then again it will be coming to this way, and you increase all the values of x in the positive direction, then ultimately you are going to cover upper half plane of this chart. That is, all circles will come inside this way, x equal to 0, then ultimately x equal to 0 means what? 1 upon 0, infinite, 1 comma infinite, and 1 upon 0, infinite. Then ultimately you will have that straight line only. Then x equal to minus 0.5, then same thing will happen for negative values to this side. That is the behavior of reactive circles. Okay, if you correlate this upper behavior, then it is representing the capacitive inductive behavior. In inductive behavior, in that numerical, first numerical, it was having all values positive. All values positive means all positive x values. Then this center line to upper side is inductive behavior. This center line to lower side is capacitive behavior, because you are having the negative x values. Now see what is happening here. From these circles, like 1 of comma, radius is this one, then this one for x greater than 0, because that red circle concept that we have already seen in last slide. Then x greater than values 0, then all circles will go to this direction. Okay, x less than 0, all circles will in the bottom sides. Okay, that is x equal to 0 is what? That is this straight line, x equal to 0. Okay, then just see linear values of r, 0 to infinite, 0 to infinite, 0 to minus infinite. All minus plus x's are within this green circle. R equal to then 1, R equal to 2, all are. Then if you see the comparison, where you are convenient to represent this linear scale or to represent this inside the circle, we are convenient to this way only. Okay, that's why it is very easy to use, but initially it takes time to understand that Smith chart concept. Once you becomes the practice, you do the practice with that one, then it is easy to represent all the problems in the form of that Smith chart. That other representation of x values also corresponding to the same thing what we have seen in that earlier, resistance value, all green, that is complete circle this, but we need to take only up to this one, blue also, red also, this only, for x equal to positive side, x equal to negative side. Mapping right hand poles to a unit circle is the Smith chart, what we have done. Okay, then this point linear scales, this point is where positive x directions, then it belongs to what? Inductive behavior. This point is x-axis, that is the resistive point. This one is capacitive point. Then all resistive points will come here. Okay, this is Z naught perfectly matched point. It will come in the center of this Smith chart. This is 0, Z naught equal to 0, Z naught equal to infinite. Then this point is low values of Z and this point is high values of Z. This is complete y-axis. According to the magnitude, it may exist to any specific points either here, here or that one. It depends on the values. What is that value? Value is not marked here. Same thing, this point will come somewhere in that upper half plane. And these point negative, these 2 points will mark somewhere here. Okay. Then all resistive behavior is on x-axis. Inductive behavior on upper half plane, capacitive behavior on lower half plane. Okay, just see this one, transformation from the complex impedance plane to the gamma circle. Then ultimately, say green line, this one. Okay, blue is same this one, and red is in lower half one. Okay, then transformation of basic shapes from the Z to gamma, that circles on the linear scales can also be represented as circle in this way. Okay, but ultimately that all things that while taking the reference of that earlier discussion, that we can easily map from that linear plot to that plot within that unit circle. That is that commonly used that Smith chart. I think now the things should be clear to you rather than to seeing that complicated graph in the very first slides. Okay, then all values are marked here for resistance, is specific resistance 0 to other side, 0 to lower side, 0 to higher side, and all reactants are also marked. Okay, then ultimately 3 different scales you will see on the outer regions of that. That is not complete. Then these are having some specific values of marked, something is visible and some are not visible anyway, that we can see while seeing that real Smith chart mapping of the admittance plane into the gamma plane, because we have plotted this one for admittance. Okay, then admittance to that reverse to that one, then ultimate just do that shifting to that one. This reference point will becomes to this one, that is rotation of this chart will be treated to like an admittance one, or other way, then this is that impedance, admittance will be reverse of that one, then only minus sign to plus sign, it will be e to the power minus, this minus can be replaced e to the power minus j pi, and this plus can be replaced with this one. It means what is that one? Only 180-degree phase shift you need to insert in the values of Z, then finally it will give you the sense of admittance. That is this way. From center to this point is if impedance, then its corresponding admittance will be this point. Okay, that is 180-degree phase to that one. Okay, like this one, that is Z in equal to 1 plus J1, and it will be Y in equal to 1 over 1 plus J1, then multiply and divide by complex conjugate, then 1 minus J1 upon 1 plus J1 into 1 minus J1, then you will get this value. Okay, then instead of rotating the reflection coefficient about 180-degree, we keep the location fixed and rotate the entire Smith chart either this way and rotate that one, then the same information you will get to this way. That's towards that summary to this one, that inductive domain center to upper, capacitive domain, and this in the resistance. Then trace how to represent that variable inductance, then how it will look like, that will be a circle, and direction of that one will be clockwise as the values are changing from 0 to infinite. Okay, then capacitance will be reverse to that one from here to this way. As the values changes, then the overall shift will be in the anti-clockwise in case of capacitance. And do the reverse process, that series inductance to shunt and series capacitance to shunt, then I think this one, okay, in this case it will come here, and in case of shunt capacitance it will be in this way. Okay, then all like conclusion of last four cases, four slides basically, this is that from here means all, if you are having a combinations of series and parallel, then ultimately this is shunt inductance to shunt capacitance and series capacitance to series inductance. Maybe some intersection points will also come into the pictures. Then illustration of adding a transmission line of length L to the arbitrary transmission line length is to be added, and how the things will be changed to that way, that we can plot in the form. Then transmission line as a function of its length, imaginary, then inductive and capacitive, resistive, and its, oh, it is not visible. Some points to be marked on that Smith chart. Okay, then ultimately it will be easy to take that one. Then how these Z1, Z2, Z3, Z4 points are represented, the two different values and that corresponding point, that you can easily correlate with this way. Then impedance coordinate, inductive, capacitive, reactance, inductive reactance, capacitive reactance. Then shunt susceptance will be represented in this way, representing the constant reflection factor, reflection directly. Then reflection equal to 1, reflection equal to 0.75, 0.5, 0.25, 0.0. Okay, then ultimately how these are represented in the form of that Smith chart. Coming to that magnitude circles, because magnitude and phase both are equally important for that complex quantity. Then phase angle, this was the magnitude, and this one is the phase, different phase, 0, 45 degree, 90, 130 degree, and all these graphs will come. This point is 0 degree, this is 45 degree, here somewhere it should be 90 degree. Where is that point? Okay, now means it is the second last one, that the diagram that we have seen there, summary means offers a compact and handy representation of all passive impedances from 0 to infinite. Impedance with negative real part such as reflection, amplifier or any other active device would show up outside the Smith chart, because it is the best representation of passive one. Okay, for if you are using an active devices, then it will be something different way. But all amplifiers, like you have seen some representation in Naoki Shinohara lecture also, something of amplifier that he has represented in terms of that one, your Smith chart. Impedance mismatch is easily spotted on the chart. The waves and reflected or backward waves in these frequency range instead of voltage and current used at low frequencies. The transition between impedance and admittance in the chart is easy to represent in this way. Reference planes in the Smith chart can be moved very easily by adding a transmission line of proper length. Many Smith charts have rulers that scales on the bottom sides of that one. Variety of quantities such as direct values of return loss can be easily taken corresponding to that point marked in that way. Few some other applications apart from that representation that can be easily done with the help of that Smith chart, squarer, then square root, tangent, cotangent, inverse cotangent, then some binary operations we can do easily. And with this one is the best possible reference for this Smith chart representation, that is original textbook of the same author. who has given that one in Bell Telephone Laboratory. Okay, you can download it easily. If it is not possible, then you mail to me. I'll share the soft copy of this one. With this, I conclude this tutorial session. If some queries or doubts are there, feel free to discuss. Any doubt? If it is not there, let us conclude this today's or day 3 of this ongoing 5-day Gyan course. Tomorrow morning we will meet again at 10 o'clock for fourth day or second last day of this ongoing Gyan course. Thank you.